尊敬的杰西兰格主席，
Distinguished Mr. Jesse Langer, Mr. Janus, Mr. Chen, Mr. Zhang, dear experts, good morning, good afternoon. I am Wang Bo, representative of China Peak Innovation Corporation Research Center. So next, let's have the matchmaking between China and the Poland Advanced Material Technology companies. So let's welcome Witold Olkowski to introduce the microwaves and high pressures for regeneration of bone tissue. Welcome.
Thank you for introducing me, and I'm very happy to participate in this meeting. But I will not spend too much time on other topics because it's running, and I will switch immediately to my presentation. Is it seen and can you hear me?
Yes, we can hear you and we can see your screen.
Okay, thank you very much. So, is this my name in Chinese? What I show here?
Yes, it's your Chinese name.
So thank you very much. This is the first time that I see my name in Chinese. I will remember it, and I hope it will be more used. So this is sonochemistry, microwaves, high pressure. This logo of our laboratory represents three energies focusing to produce nanoparticles. And new materials were always in the history since thousands of years key factors for civilization progress. And since about 50 years, nanotechnology starts to play a contribution to human development, where the main variable is the structure size and not only the chemical composition or phase composition, like was it in the previous times. And so size control of structure is crucial for successful use of nanotechnology for the benefit of humanity. Now, what we want personally in our laboratory, we dream to see happy patients thanking us for being healthy again after serious bone injuries. And I truly hope in collaboration with China, we can do more and better in that direction. Now, nanotechnology likes, likes low temperature processes, yes, because nanostructures are thermodynamically not stable. There are tremendously surface energies and stresses and pressures, which give a big driving force for growing of the grains and the structure into bigger structures. So high temperature processes are not favorable for nanotechnology, and therefore we explore use of special technologies to reduce the mean or average temperature of the processes. And microwaves. Microwave servothermal hydrothermal synthesis is to produce nanoparticles with program size, saving energy in green condition. Especially we focus in this talk on hydroxyapatite, which is a material which is a component of human bone. And sonocoating or using ultrasons will be presented to coat materials with nanoparticles at room temperature. And high pressure permits to compact nanoparticles into bulk nanoimplants. So microwave solvothermal synthesis to synthesize and the two other technologies to make from this nanoparticle useful materials. So first, shortly about microwave servothermal synthesis on the example of hydroxyapatite. We developed, so this is actually the principle shown here. We have a chamber, which is here, which resists about 6 megapascals, 60 atmospheres. and pressure and microwave energy is applied to heat the components which is in this chamber. So with the microwave, we can very quickly heat without big gradient in the vessel. If we would like to heat with this speed in a conventional way, we would have very hot walls and cold liquid. With microwave, is the other way around. And this is a long year of work to develop the reactors. We work together with one of the institutes which Professor Langer told, from the Łukasiewicz Network Industrial Institute for Sustainable Technology, to make such reactors. And now we have a new version of this reactor. We call it MSS4 because this is type 4. And Teflon vessel of this volume 0.3 liter and heating rate up to 1.8 Kelvin per second, yes? And the process duration can be controlled with a 1 second time resolution. And you can see here a modeling exercise where we show that indeed the energy is developed inside of the vessel first, whereas the vessel walls are cold. And here is a robot arm so that we can put in, here are the high pressure vessels too, and we can prepare the vessels with the top straight, and this robot arm insert them in the high pressure vessel, and is closed, and the process is automatic. The robot arm can also shake the liquid, and when it is over, it can remove the vessel, the hot vessel, from the chamber. All the preparation are done in a clean room, of the liquids for synthesis in a clean room, and then separation of the powder, which is produced, is also done in the clean room, because we apply for clinical applications. And here is an example. We produce hydroxyapatite, which is a component of human bone. And we can control precisely the size. So the type 1 has 8 nanometers, and type 2, 10 nanometers, type 3, 15, 23, 30, or 43. When you compare with the animals or humans, we see the type 1 is almost identical in structure. It's an X-ray diffraction pattern with a natural hydroxyapatite of a duck or beef. And also human. Whether the 6 is more similar to hydroxyapatite in the tooth enamel, which is a larger grain size. And you see with what a precision, by controlling the time in the reactor from a few seconds to a few minutes, we can stop the reaction and produce exactly the grain size we need for the given application. And here are some examples of difference of property. For instance, the powder was put in water, and we measured the calcium ions concentration. That means how the powder dissolves. And we see the type 1 dissolves much quicker and gives a high calcium concentration. Whether the type 6, which has a very much bigger grain size, 40, but let's look at the bigger means 45 nanometers. This tells at what level of technology we are, have a much lower calcium dissolution rate. So when we want to make an implant, for instance, we can control by changing the grain size, how quickly it will dissolve and how active it is. Now, we develop this material, we offer this material now for veterinary applications. It is produced in clean conditions, and the veterinary regulation permits to offer such material as we produce. For the moment, we give them to the veterinary doctors for free in exchange for information on the results of the operation. And second, I will now tell about coating using this powder to modify surface. So if we have a polymer surface like this scaffold 3D printed, for the cells it's not a friendly material, it is a polymer. But if we coat it with hydroxyapatite, the cells recognize it as a friendly material, biocompatible material. And the coating is using by ultrasonic technology. It is a paradoxal because usually ultrasounds are thought to clean materials and not to make layers of them. But it is a process discovered some time ago and made popular by Professor Aharon Gedanken from Israel, our very good friend. And it is claimed that when a cavitation bubble collapse, the ultrasonic energy leads to local evaporation of formation of vapor bubbles, which is a process called cavitation. And when these cavitation bubbles collapse, they form a jet that throws the nanoparticle toward the surface and contribute to make a layer. The process is at 30 degrees only, but it can be at 25 or 20, but it is just a convenient temperature, short time, and in water as a medium. And here are some examples of coating, some fibers, a 3D printed scaffold, a titanium surface, a glass tube, a polymer surface. And here is an example of bioeffects. Yes, we took a PCL scaffold coated with hydroxyapatite using this method in rabbits. Yes, a hole was drilled, the scaffold was inserted, and this one is a non-coated scaffold after 6 weeks. And this is a coated one. You could see that histopathology shows that the pores between the fibers are completely filled with bone. And the scaffolds start to decompose also because of change of chemical compositions. So for the moment, we had now even over 100 successful operations, never any claim of any negative effects. In dogs, even 4 cheetahs from Warsaw Zoo, in horses, and even 1 owl, because we have an interaction with the Warsaw Zoo where the doctors are love very much the animals and want to help them. And this hydroxyapatite, when mixed with blood or marrow, forms such a paste which can be easily pressed in the bone gap. And here is shown one case as just a powder is introduced in the bone gap directly without mixing. And here is followed the process of bone regrowth. And here is a 3D printed scaffold. Also, it is seen bone ingrowth. And also horses. Yeah, for now the society in Poland becomes more rich, so that, for instance, such an operation for a dog costs about 1,000 euro or 1,500 euro, and the doctors tell that they have continuously patients. So that means the society now, the attitude to animals changed because the people can afford to spend a lot of money to help the beloved pets. But in the case of a horse, it's already much bigger money because a horse can cost $100,000 or $500,000. And we have already 6 horses operated with our materials. And also, I mentioned Chetax from the zoo, which is value is very big, of course, but it's difficult to tell in money. And here we have a case of a horse from France, which was transported to Poland for this operation because the horse broke these 2 teeth, and the doctors were very surprised that after 4 weeks, the horse could already eat carrots. And finally, some high pressure, where we try to, what is the problem? That the present implants, which are used, metallic, are too hard for the bone, and there is a gap that forms over a long time between the implant and the bone, and the polymers are too soft and not very friendly for the body. So one is looking for a mixture of nanoparticle with hydropolymer. And we use a technology which does not need any solvent. We just put powder and polymer in a mill at liquid nitrogen temperature milling. And we get such a powder, and we see a very strange phenomenon of very good adhesion between the polymer and hydroxyapatite after this milling. And this powder can be then pressed under high pressure, and we get composite that has a mechanical property close to the natural bone. But here we have a lot of work to do to study how such a material would behave in the animal body or human body. So in conclusion, yeah, we have big advantages for application in nanotechnology of microwave synthesis, ultrasonic coating, high pressure compression, because we have green processes and we have reduced mean temperature so that we can very precisely control the nanoparticle size, and then you make coatings or compaction without changing the structure of the nanoparticles. And we have a key to application of nanotechnology because we have very precise regulation of nanoparticle size and quality. And we have already happy patients. I mean, owners of animals, of pets, are happy because the animals also are happy because they have less suffering. There are many issues in front of us, like nanosafety for clinical applications. We study now the nanosafety biocompatibility to make to fulfill the requirements for clinical application. But there are also many business issues, like production engineering, automation, artificial intelligence involvement for further scaling up and development of this technology. And frankly speaking, we are not very competent in business issues which are related to bring such material to market. So here we need also support in this respect. And I would like to say that we have also a very recently a lot of funding from various projects, Polish and with industry and European, and we have now also constructed a clean room and achieved ISO 1385 certificate that is a requirement for reproducible production according to medical devices regulation. Thank you for your attention.
Thank you very much for your presentation, for your roadshow. And now I would like to invite
Professor Marius projects to talk about super strong fasteners made from nanocrystalline